All right, folks, let's get settled. All right. Now, so this unit is an introduction to astronomy, and again, I haven't taught this in quite some time, and various teachers I've borrowed some notes from, and they're done in various ways, and so I kind of found that I needed to kind of reorganize the information for the way I want to teach it. So I'm teaching this in a slightly different order than maybe some of your peers in some other grade 9 classes. So things may look a little different, which is fine. In terms of my background on this, at first year at Western, I took a course on astronomy. There are two versions of astronomy courses you can take at university. There's one that isn't really for true astronomy people, where it's all about looking at the stars and all that type of stuff, and that's kind of fun. And then there's something that we would call astrophysics, and I took the one on astrophysics, a very neat course, a very difficult course. So I've taken quite a bit of information on this particular subject. So I find I'm torn on how much information to tell you guys and what to give you, et cetera, et cetera. Anyway, so there's a little bit of a background. So I do have some information on this in order to answer questions. It's not like ecology where I struggled greatly with that. Having said that, this is going to be more of an information kind of quick unit. In other words, we're not going to be doing a lot of labs. Well, there are no labs. And that's because, well, we're going to be talking about stars and things and planets, and it's kind of hard to go to the stars and do a little experiment. We will be talking a little bit at the very end about constellations and what we see in the sky, and that's something I suppose we could do an experiment with. But the problem is it's hard to see the stars during the day, so it's tricky to get outside and actually see the stars. But I will be introducing you again to some cool apps. Again, our phones are awesome at giving us kind of an augmented reality of the sky, kind of like our Seek app, except for stars. And it's not like I'm going to have you do an assignment again. If I were to teach it again, I might create one, but at this point, I'm really just going to be introducing it to you. Okay, so there's a little bit of a background. So let's start simply with a definition of what astronomy is. And as I imagined this unit, again, logically in my mind, I imagined it as starting here on Earth, because, well, we're here, talking about the properties of the Earth, and then working our way out from the Earth to other, what we call celestial objects, other objects in space, as we would encounter them as we go out in space. Practically speaking, humans have made it to the moon, and that's it. So in a reality sense, humans have been in orbit, lots in orbit, the International Space Station, all of the space shuttles, and the early capsules. We've been to the moon, but that's it as in terms of humanity. We've sent probes to all kinds of planets, to all of the planets in the solar system. All right, had a close look at them. And there are some probes that are still going, some of the earlier probes that are still going past the farthest reaches of the solar system and into what we would call interstellar space, the space that's found between stars. What I'd like to do right now is just make a list of the order of things in which we encounter as we go out into space. And I'm going to cheat a little bit because I've created a little list on my PowerPoint here. I just got to get this out of the way. As we leave the Earth, what's the first beyond Earth objects we would encounter? Yep. So the atmosphere is the air, all right? And I'm not going to count that as part of stellar objects. It's very important to us, but we're going to get past the atmosphere. So let's get past the atmosphere. What do you think the next thing is that we're going to encounter? Yep. So the moon is a great answer. The moon is what we call a natural satellite. It's in orbit. But part of this unit is also to study artificial satellites, satellites in space that help us, our GPS. So that's the first thing I want to put is satellites. Satellites, and my spelling's going to be terrible, but that's okay. And exactly what is next, you're right, the moon. And they both fall under satellites, and we'll talk about the moon. I think tomorrow we're going to talk about the moon. Today we're going to talk about the Earth and its behavior in space. Then we'll get to the satellites and the moon. And the way I kind of organize my unit is that we're going to start at Earth and we're going to work our way out. Once we get beyond the moon, what are the next objects that we may encounter as we are moving away from the Earth? We've gone past the moon. What are we going to encounter next? Yeah, Jenny? Planets, you bet. Planets? Yeah, you put it right there. That's awesome. Thank you very much. Planets, and in this case, if we were to keep going, what else might we encounter? Yep. Excellent. So the planets in the asteroid belt, that's excellent. So you've done some work on this in elementary school then, right? So we've got our interior planets, right? Then the asteroid belt and then the gas giants. We'll talk about that more later. I'm not going to put that in there, but you're right. You're working your way out. I want to talk about one other thing here. Yep. Careful. We're not to other galaxies yet. I want to put one thing in the middle here. I want to put our sun, because we haven't talked about it yet. But, we've got planets and then the sun, right? And now we're going to be beyond our planets and the sun. We're not to other galaxies yet. That's too big of a structure. We encounter something else first. Yep. No, meteors are different. Meteors are tiny little objects which actually land on the Earth. So we've got to get even further out. Yep. Yep.
Other planets have more than one, right?
Some can, yep.
So would you encounter them as well?
You could, but we're not going to worry about that. We're just going to worry about the Earth-Moon system in this particular unit. But you're right, other planets would have other moons. Yep. Comets, you could encounter comets. I like that one. Beyond the sun, you could encounter comets. Comets, 2 M's? No. Comets. My arrow is going around to the other side. That one's not even on my list, but I like it. That's in the right spot. What are we encountering next? Yep. Nope. Asteroids are within the solar system. They're in the asteroid belt. So no, we don't do that. We're now beyond our solar system. We've gone past the furthest planets. We may encounter a comet. Keep on going. What's the next thing? Maybe. Yep. Sorry? Stars. Other stars. Stars. So at that point, you're encountering maybe some dust or some gases that exist in between our star, and then ultimately we encounter another star. So as we move our way out, we encounter more and more stars, and now we're getting to bigger and bigger structures. Let's say now we go past lots of stars. Now what do we encounter? Yep. You're right, there'd be lots of darkness, but I'm not going to study darkness, because darkness is not very exciting to study. Once we get past the stars, what's the next larger object that we encounter? Okay, at this point, we're talking about galaxies. Galaxies. All right, so galaxies are huge structures that contain billions and billions and billions and billions and billions of stars. So if we leave our galaxy, any idea on the name of our galaxy? What's the name of our galaxy? Yep. Milky Way. We'll talk about why it has that name. And once you leave our galaxy, you would encounter other galaxies. I think Andromeda Galaxy is the next one that's closest to us. And if we were to keep going further and further away, you then have all kinds of galaxies. What would we call the next larger structure beyond the galaxies? The largest structure. The universe, that's exciting. The universe, it's funny, uni stands for one. Is there anything beyond the universe? Is there anything beyond the universe? Interesting question. Physicists and cosmologists study the skies. There's recently been some theories called string theory, which tries to explain the physics of the universe, and that expands into something called M theory, which is called membrane theory. And one of the theories is that universes can be created when these four-dimensional membranes run into each other, and therefore, if universes can be formed, then could there be more than one universe? Some people call this the multiverse, as opposed to universe. We're definitely not going to talk about multiverses other than just this. But some scientists believe, cosmologists, that there's more than one universe, that there's all kinds of universes, and that they have slightly different rules, all right? All you people who have little bits of candy hidden in your pockets need to stop eating them, all right? You're distracting me. Don't distract me, please, all right? Okay, so that's kind of the progression from the smallest, us here on Earth, moving our way out to larger and larger objects. All right, so these are the things that we want to talk about throughout this entire kind of universe. And for today, we're going to land ourselves back on Earth. Okay, so let's come back to Earth. We went all the way out to the furthest reaches of the universe, and now we are back on Earth. So let's talk today a little bit about orbital motion and orbits and the way things behave in space. All right, these things, the term we use is celestial objects, objects like the Earth around the sun, or perhaps the moon around the Earth, etc., etc. So let's talk a little bit about that. So the Earth is in orbit around the sun. The force of gravity keeps the Earth in orbit around the sun. So let me get this out of the way. Yes. You cannot write ahead on this, folks. You can try to, but it's going to make no sense whatsoever. You're right, they do. Yeah, and could you take the music out of your ears, please? So you're not going to be able to write ahead because I'm going to do a lot of writing on the PowerPoint. So you can't write ahead. You got to pay attention, you got to listen and draw what I'm going to draw. Okay, so the force of gravity keeps the Earth in orbit around the sun. We've seen linear relationships. You've seen a whole bunch of different equations that we then can use to take the slope to study that. And you guys are doing that in math, right? You're learning all about linear systems and how slopes can be used for calculating things, all right? And that involves pretty straightforward equations like R equals V over I, right? Rise over run. There are many other types of equations that we can have in physics, and gravity is an example of one of those. Let me give you an example of the equation for gravity. The equation for gravity, G, all right, is equal to a very tiny number called the gravitational field constant, big G, times the mass of the object that is exerting the force of gravity, divided by the distance between it squared. All right? And this represents something like the sun. I'm going to put here S for the sun. And something like the Earth. And I'll put a little E in there for the Earth. And in between these two things, there's a distance called R. like a radius. And if we put the mass of the sun in here, then, and we put the radius of that distance, we can figure out how much gravity is pulling on it. But notice that this radius has a square. So what that means is, I'm now going to draw a little graph here, just like this, a sketch. So just draw a sketch of a graph there. Doesn't have to be perfect. That if I have the radius out here, the r, and radius, and I have that force of gravity, the force, all right, that it does this. It starts up here and it drops off really quickly and goes really low. So it's not linear, all right? It's got a curve to it, and it even drops down as you get further away. So if this was our object, like the sun or the earth, it doesn't matter. This could be like the sun or the earth. Well, let's call it the earth for now this time. Let's call it the earth. And if we were on the surface of the earth, right, at the surface, there would be a lot of gravity. Notice that the force is high. This is strong gravity. So here at the surface of the earth, all right, we're close to the surface of the earth, and we feel strong gravity. What happens to the strength of the gravity as we get further and further away from the earth? Danton? It gets less, and it gets less very quickly. So if we were far away from the earth, so if we're out here, and I'm going to put a line way out here, so if we are far from the earth, then we have weak gravity. All right? Notice the line curves, but never quite gets to zero. It means that there really is never zero gravity. It just gets weaker and weaker and weaker and weaker the further away you get from an object. Now, some of you are going to say, but I thought there was no gravity in space. There is gravity in space. It's just if you're far away from a big object, it can be such a small amount of gravity that you don't even realize it. You don't even feel it. Okay? So it drops down very quickly. All right? Now, you do not have to worry about this equation. Don't worry. All right? Don't worry. Don't mind my scribbling on there. Don't worry about it. I'm not going to ever ask you to calculate that. I just wanted to show it to you so that you can see that it's got this dependence on the distance and it goes down very quickly. Okay? So as we leave the surface of an object, whether it's the earth or whether it's the sun or whatever it is, gravity decreases greatly. All right? You guys might know what happens. What's the force of gravity like on the moon? What's the force of gravity like on the moon? Anybody study this or tell anybody or learn about this? Does anybody know? The moon's mass is much smaller than the Earth. That means this m is a much smaller number, and therefore the gravity given off by the moon is much less than the gravity given off by Earth. So therefore, the force of gravity on the moon is about 1/6, which is why if you look at video of the astronauts on the moon, that's why they can jump around and move around so freely, because the force of gravity is much weaker. It's a much smaller object, and its radius isn't as great. Okay, let's keep going. I'm not going to use that extra slide because I've changed my mind. Let's talk about motions of objects in orbit. Okay. So let's talk about orbits. There was an early astronomer by the name of Johann Kepler. I'm going to say around the same time as Galileo, maybe a little earlier. This is early 1500s, and he studied the orbit of, or he studied the motion of Mars in the sky very closely, and he learned that there's three important rules when it comes to objects in orbit. So if I have, again, my object in the center, and I'm just going to put it right there. This could be the sun, this could be the moon, this could be Earth. It doesn't matter what it is. It's some large object M. And we're going to put an object in orbit around it, a smaller object. All right? And when objects are in orbit, they trace a particular path. Does anybody know what path that might be? What shape the path might be? What do you think? Yep. You might think it's a circle, and some of them do, but there's a more general shape. Yep. Yeah, it's an oval. We call it an ellipse. It follows what we call an ellipse. So it sometimes has this kind of oval shape. All right? That's not that great. It's not bad. Notice how I put one end a little closer than the other end. Please draw it like that. So draw that kind of oval shape with one end a little closer. So all orbits follow an ellipse. An ellipse is a fancy way of saying an oval. All right? And the perfect ellipse is a circle, which means circles do count. They can be circles, but they're rarely circles. They're usually these ellipses. You always have a closer side. This is the closer side. Closer. All right? And that closer side is called the perigee, and I want to spell it correctly. Now it's called the perigee. It's two E's. Perigee. So perigee is when it's closest, and then there's always a side where it's farthest away, and that's called the apogee. And the way I remember it is away is apogee. All right? In actual fact, the Earth around the sun is an ellipse, and yesterday was apogee. No, wait a minute, perigee. I got it backwards. Yesterday was perigee. Yesterday, our Earth was closest to the sun in its orbit. All right? And it has nothing to do with the seasons. The seasons are something else, and we'll talk about that in a moment. All right? So yesterday was perigee. We were the closest yesterday. All right? Which means the sun would have looked a little bigger if it was out. Wasn't really out much. So they orbit as an ellipse. Another rule that's very important: when the object is close, it moves fast, and when the object is far, it moves slowly. When close, the object moves fast, and when far, it moves slowly. All right? Yep. Solar eclipse has nothing to do with apogee and perigee. We will talk about solar eclipses tomorrow. Okay? All right? So, because yesterday we were close, the Earth was moving the quickest in orbit. All right? And in 6 months, it'll be away, and it'll be moving slowest. So here it moves fast, and here it moves slow. All right? Okay. There is one other kind of rule that goes with it that's very complex in terms of mathematics, and we're not going to worry about that. Yes, how can I help you? Okay. Now, the Earth's orbit is pretty close to being a circle. If we were to somehow rise above the sun and look at the orbit of the Earth and just kind of look at it, it would look circular. It wouldn't be far off from being a perfect circle. Objects that have orbits that look like really flat ovals are things like comets. They go great distances, way out to the end of the solar system and then really close to the sun, and they're super flat ovals. So we can have objects that have these crazy flat ovals that go very slow when they're way out there and go very fast when they come around the sun. And then we can have things like the Earth, which are almost perfectly circular. All right? But there is a slight difference. Okay. Click. I did the example of the Earth. That's fun. Let's write down some definitions. So, at this point, we've talked about gravity, how gravity gets really weak when we're far away, which is why things are moving slow, because the gravity's really weak. It's hardly pulling on it. When we get close to the perigee, it's moving fast because gravity's pulling it around, making it go fast. We know we're going around in this orbit, around and around. So let's now go over some terms to define this. The orbital period. It's given the letter capital T. In physics, the word period simply describes anything that happens over and over and over again. It means that it is periodic. We encountered that when we talked about the periodic table. I'm going to draw a picture to illustrate these two things. So I've got some space on the side. I'm going to use the sun, Earth in this case, because now we're going to talk a little more about the Earth. So if I here have the sun, there's our object that is applying the force of gravity. Here I've got our Earth, E, and the orbital period is the time to go around once. All right? What do we call the orbital period for the Earth? What do we call that time it takes to go around the sun once? Yep, that's a year. 1 year. Right? Sound familiar? Yep. Where are you seeing?
Because you said that an orbital period is 1 year. So.
Yes. Yes, correct. So I don't know the historic the historic origin of the word year, but early peoples, and I'm talking way before even science or scientists, they would have realized that there's a yearly kind of repetition in the seasons, etc., etc. We now know that our seasons are due to this time going around, and so yes, that's where the term year would have come from. Correct. Orbital radius. Oh, we've talked already a bit about radius. That's that distance between the two objects that one is going orbit around and the other one is kind of stationary. It's not really stationary, but it can be. Okay. Notice it says average distance, and that's because if it's not a perfect circle, it might be a little further at apogee and a little closer at perigee. So we take an average to get that orbital radius. Okay? All right. A few more terms here. Axis of rotation. So So the Earth, not only does it orbit, but the Earth rotates on an axis. I'm going to draw a picture for the first two, and then I've got a separate picture for the bottom one. Now, all of these terms can be used for all of the other planets, right? So Mars would have its own orbital period, and it would have its own orbital radius, right? Mercury, Venus, etc., etc. And when we talk about the planets in a couple of days, we will use these terms to describe them, right? So again, Mars has its own Martian year, right? Has its own orbital radius. Same with axis of rotation, period of rotation, axis tilt. So, axis of rotation. I'm going to draw the Earth here. All right? And this is my rendition of the equator. Okay, so that is the equator. And I'm simply going to put a line at the top and a line at the bottom as if I've got a couple of pegs or something sticking out of the top and bottom, north and south poles. And that is the axis of rotation. So the axis of rotation is that imaginary line from the poles, 90 degrees to the equator. And so that is the line at which it rotates around. Period of rotation. If we had a particular point on Earth and we determined how long it would take to get back around to that specific spot, that's the period of rotation. How long it takes for that thing to rotate once on its axis. What do we call this period of rotation? The time it takes to go around once. Yep, that's a day. That is 1 day. All right? So again, the Earth, we know our day is about 24 hours. But each planet will have its own day, right? Some rotate fast, some rotate very slowly. All right? Axis tilt. It's the angle at which the axis is tilt compared to its direction of motion. The Earth doesn't go around the sun straight up and down. The Earth goes around the sun on a slight angle. So the axis tilt, if I were to draw a picture of this again, that's my rendition of the Earth. This time I'm going to put the axis on an angle. Again, there's my equator. All right? And I am going to put a dashed line straight up and down to represent this angle here. That's how much the Earth is over on its side. Again, all planets will have a slightly different axis tilt. I don't think there are any straight up and down, and I think there's one that's almost completely sideways, 90 degrees. I don't have them memorized. Okay? For the Earth, does anybody know what the axis tilt is? Anybody know what that value is? It's very important for the Earth. It's what results in our seasons. Yeah, what do you got? You're checking it? Doing a quick search? No? 23.5 degrees. 23.5 degrees. Right? 23.5 degrees. Anybody taking geography right now? Geography? Have you guys talked about the Tropic of Cancer and the Tropic of Capricorn? You'll notice that they're 23.5 degrees. Longitude, whatever, one of the tudes, something tude. Okay, I haven't done geography in a long time. That's the reason for it, right? That's the reason for it. The axis tilt creates those lines, and that's the kind of furthest north or south the sun appears to be. All right. How are we doing? Again, this is just definition time here. Yep. That's okay. Yep.
You know how it all spins, and they all spin the same way?
Most of them do, but there's the odd one that goes the other. There's one that goes the other way, if not two. But I think maybe just one. I don't know of all the. We're going to do the planets in a couple of days, and we'll look at some of that information. But you're right; they all kind of spin the same way. I can explain why, but maybe we'll save that for when we talk about the planets. Okay? Yes. We'll talk about that when we get to the planets. We'll talk about that when we get to the planets. We're still on Earth. We're not at Pluto yet. We haven't left. Well, we'll discuss Pluto's demise. Well, I guess it's not dead, but no. Are we good to go? Good to go? All right. Again, we're talking about the Earth at this point. So let's talk about the seasons then. Okay. So it is the axis tilt that results in our seasons. So even though we are currently close to the sun, yesterday being the closest, in the winter, the northern hemisphere points away from the sun, and so we don't get very direct sunlight. All right? So even though we're close now, the tilt of the axis has a greater effect on our weather than the fact that we're closer, we're at perigee. Yep. Because 6 months from now, right, well, December the 21st, whatever it was, then we will be pointed towards the sun and they will be pointed away. Correct. So, in my picture, and again, I'm very much about pictures here. Here we're going to have the sun. And this is not going to be to scale. This is going to be a tiny little sun. And I'm going to put a fairly large Earth over here, and I'm going to point that axis away. Okay? So there's our north, and there's our south, and there's our Earth. And so you can see here that the sun's rays are going to hit more directly on the southern hemisphere than they are on the northern hemisphere. So in this case, the north is pointed away from the sun. And if the north is pointed away, we're not getting as much direct sunlight. What season are we talking about here? Winter. Do you guys do this stuff to death? Like, do you guys do this like crazy in elementary school, that type of thing? So the date in which this takes place, December 21st or 22nd, depending on whether it's a leap year or not, that type of thing, 21st. Does anybody know what it's called, technically? The winter solstice? I don't know how to spell solstice. S-O-L-S-T-I-C-E. S-O-L-S-T-I-C-E. Hold on, let me get to the other side of the orbit. Zoop, zoop. Don't worry that the Earth hasn't shrunk in 6 months. North towards the sun. All right, the north is pointed towards the sun. This is happening, what, June 21st? What's it called? Summer. You guys know this stuff well. Excellent. Solstice. Did I do that right? Yep, summer solstice. And I'm going to just do this type of thing. And over here, we've got the various equinox, right? So I guess if we're heading, I really don't know if I got the direction correct, but that's okay. We'll go this way. If we're going, well, wait a minute, summer, so winter to summer, so I guess this is March, right? because I've been going from winter to summer. March what? No, 22nd, 21st, 22nd. It's not a solstice, it's an equinox. It's the vernal equinox. Vernal equinox. What's true about at the vernal equinox? What's true about the day? It's sunny but not sunny. Sunny but not sunny. I like that. That's almost like doing the weather. And Jenna's going to do the weather. Here we are at the vernal equinox. Today is sunny but not sunny. What do you got? It is indeed. It means the same. What's the same? What's equal? Yep. What's equal? Yep.
Is it because it's late? Is it equal to the one, like the fall one?
Kinda. Yep. Yeah.
The hours in day and night are the same.
Yeah. The hours of light equals the hours of dark. Right? So light / dark is equal.
Is it the same for the other one?
It is exactly the same for the other one. This is going to be what? September 21st. This one's called the autumnal equinox for autumn. Autumnal. A-U-T-U-M. Autumnal equinox. Again, light and dark are equal. Light / dark equal. Okay? Light and dark are equal. Because what sucks about December 21st? No, not daylight savings. It's the shortest day of the year. Shortest amount of sunlight, right? And what's awesome about June 21st? It's got the most sunlight. And no, we can't save daylight, Robert. We can't just like put it in a bank and bring it back out. Okay, how are we doing so far? One last thing for today's lesson. Precession, something called the axis wobble. Oh, and I meant to get a top. How many have played with a spinning top when you were kids, right? Have you noticed that when the spinning top starts to run out of energy, it starts to do that type of thing, all right? No, it's not because the Earth is running out of energy. No. So the reason a top is the reason a top, oh gee, this is a complex thing. The reason a top starts to wobble like that is that the base of the top is interacting with the desktop or the tabletop, and it's transferring some of its momentum to the Earth. Oh man. Again, this is a complex physics problem. So the Earth is also transferring some of its momentum to the top, and so it starts to wobble, and as it slows down and loses its energy, the wobble gets greater. The Earth is not transferring any momentum to anything. Well, it is kind of with the sun, but it's got this kind of wobble like a top that takes 26,000 years to complete. If I were to draw it, it would look like this. Again, there's my Earth. There's the axis. There's the equator. And in the end, this axis makes a kind of wobbly circle like that. And this bottom one will do the same except in the other direction because it switches. That 23 degrees points in a different direction. So that means in 26,000 years, when it's winter here, it's going to be summer because it's now pointed the other way. It's pointed that way, and then it's going to change back. So our position of winter and summer is always slightly changing. All right? So again, this guy's going around this way. I guess I'll put it like that. And so it's wobbling around like that. Scientists believe that this is what's responsible for ice ages. right? As that wobble changes, we're facing the sun in different ways, and it results in a little colder Earth, right? Because right now we're closer to the Earth. If we had winter, say, when we're further away, that combined effect might affect things. Okay, you can see here that all I've given you for homework is 3 problems. Okay, so you'll notice there's not much, which means really your homework, once you're done this, is starting to think about your demonstration of learning, culminating activities, if you are eligible. All right, if you're not eligible, you still might be starting to think about reviewing for the exam. All right, so you'll notice I've got a little less homework these days, and that's because you need to start thinking about either culminating activity if you're eligible, or you're thinking about reviewing for exams if you're not eligible. Okay? All right, just one second. Let me stop my recording.